All right, so hi everyone. Welcome to the first IAIFI Colloquium for spring 2026. I'm very excited to introduce our speaker today. Professor Roger Melko is a physics professor at the University of Waterloo, where he holds a Canada Research Chair in Computational Quantum Many-Body Physics. He is also associate faculty at the Perimeter Institute for Theoretical Physics and holds additional affiliations, including with the Institute for Quantum Computing and the Vector Institute for Artificial Intelligence. He earned his PhD from UC Santa Barbara and was a Wigner Fellow at Oak Ridge National Laboratory. His research focuses on developing computational tools to study theoretical quantum many-body physics, and today he'll discuss how large language models can help tackle these questions. Please join me in welcoming Professor Melko.
Thank you very much. Thank you, Victoria. How am I in terms of, can you hear me at the back?
Oh, and if at any point you have any questions, please raise your hand and I'll pass you the microphone so that folks on Zoom can hear as well. Thank you.
Right. Welcome to those of you on Zoom. And, thanks so much to IAIFI for inviting me. It's always great to visit Boston, great to visit MIT. Just so I kind of get an idea for my audience, any condensed matter theorists in the audience? Couple? Does that count? Recovering? Oh, ouch. What about quantum computing people, quantum information? I know one. Couple? Okay, all right, good. Just so I know kind of maybe what I'm going to talk about here. This is my group at the University of Waterloo and the Perimeter Institute, what we call the Perimeter Institute Quantum Intelligence Lab, which is our, I guess, AI effort that's been going on since about 2018-ish or so. A real great group of people. You'll recognize some of them. I'll talk about some of their work. What we do in my group very much is we think about condensed matter and quantum computers as sort of quantum many-body systems. And we think about how, I guess, AI and machine learning writ large, I guess, influence our studies of fundamental, many-body physics. And so as an outline for my talk, I'll break it up into three parts for those of us with short attention spans. Quantum simulators and quantum data. So I want to talk about quantum computers as instruments of simulation first, okay? Then I will turn to a specific platform based on Rydberg atom arrays, which provides data in some sense for models that we train. And then if that doesn't entice you or you find that boring, I'll end off with a little bit of a discussion on critical points, quantum critical points, and universal scaling that I believe is relevant for kind of language models and writ large, AI writ large. So kind of breaking things up into three parts. Let me start with quantum simulators. And a lot of what we do in my group, again, is thinking about the data that comes from quantum computers. And quantum computers are still very much, experimental devices. Let me put it that way. And they have many use cases. We believe they have many use cases. And I think we can agree in the field that their kind of most immediate interest is in simulating other quantum systems. And let me just kind of frame this with sort of a standard slide I always show, which is, the original vision of Richard Feynman for a quantum computer was to simulate processes in nature. And so I'm a condensed matter theorist. I'm trained in the tradition of, I guess, high TC superconductivity and the Hubbard model and so on. When I was a young grad student and postdoc, sitting where you guys are today, I mentioned this before, somebody came to me and said, cold atoms are going to, make you completely obsolete. Cold atoms will emulate the Hubbard models that we don't need computational theorists anymore. And I got to say, it really hurt. And I've really been thinking about that for the last 20 years. And so part of, I think, the idea of quantum computers is to emulate processes that we have kind of a poor understanding of. So high TC superconductivity, starts with experimental observations of high temperature superconductivity through various, chemical and physical investigations. You can kind of pare down the lattice structure that occurs in these materials. And then, further abstraction leads to the idea that you have some sort of model of the fundamental process. That's what we call the Hubbard model, which I'm not going to talk about any more past this slide. And then I think the kind of rough idea behind a quantum simulator is to emulate the interactions that we believe, the microscopic interactions that we believe leads to that macroscopic phenomena, in this case, superconductivity. And the most highly controlled quantum systems, quantum computers, let me use those words interchangeably, are the interactions are tuned. So this is an old figure when we're thinking about sort of standing light and cold atoms and so on. But the idea is that we can tune interactions in some of these highly controlled systems to fully emulate the interactions that we believe are going on in the material system. That control allows us to tweak knobs so that we can find out and measure the underlying mechanisms for things like superconductivity and so on. And they occur in these highly controlled, for example, this is Griner's quantum gas microscope at Harvard. And I just want to point out that here at MIT, Harvard Center for Ultra Cold Atoms, I think a lot of the data that we work on in my group really comes from the Boston area. So you're really at the forefront of science in this idea, in this, this field of quantum simulation or quantum emulation. Cool. Now, we're not quite at the Hubbard model yet. We haven't solved room temperature superconductivity, which is in some sense the mission of the field. But I would argue that perhaps more amazing things have happened in recent years in the area. And by in the area, I mean in the field, but also in this area, in the Boston area, MIT at Harvard. And I want to point out this paper here, Quantum Phases of Matter on a 256 atom programmable quantum simulator. We have one of the PIs in the audience. This was really an experiment that showed that you can realize in a very precise way not only phases of matter, and again, it's not superconductivity, but it's some other phase of matter. There's enough atoms that are under enough control in this quantum computer that the experiment can stabilize a phase diagram. And I'll explain more what this phase diagram is and what RB and delta and all these parameters are. But really, there's two phases, a disordered phase and what we call a checkerboard phase here. And that can be stabilized, and it can also be studied using the data that comes out of that device. And I also want to point out that you can stabilize something even, I think, more interesting than just a phase of matter, and that's a phase transition between matter. So here we have two different phases. This is near absolute zero or at zero temperature if you want to abstract away. And what we realize here is what's called a quantum critical point. What's interesting about critical points and phase transitions is, of course, the idea of universal physics. And so there's universal phenomena that can be associated across all sorts of scales of space and time and in different matter and material systems and so on, that are unified by certain theories which give us universal parameters. I'm probably speaking to the choir for a lot of you. But it's really remarkable in some ways that you can realize the finite size remnants of quantum critical points in not even today's experiments, experiments from 5 years ago. And there's, buried in this paper is, I think, a really kind of amazing sentence. The phase transition between these two phases of matter in this quantum computer is expected to be in I can't say that word, the quantum Ising universality class, the Wilson-Fisher fixed point in 2+1 dimensions. And as pointed out, it's never been previously observed. This is the first time that a 2+1D, so a three-dimensional, but a two-dimensional quantum system, realizes this 2+1 dimensional, fixed point in the RG sense in a real experiment. And I mean, for all the promises of quantum computers, from breaking 2048-bit RSA to solving the Hubbard model, I think it's really incredible that we have these platforms that give us, direct access to universal physics. And I would argue they give us probes into a world of quantum phases and phase transitions that we can't realize in any other system. So there's reasons that the 2+1D Wilson-Fisher fixed point hasn't been seen in a material system or a matter system before. But in the last decade or less, we made a lot of progress in looking at other types of exotic phase transitions that can be realized only in quantum computers. You might have heard of measurement-induced phase transitions, for example. So I really view a quantum computer as almost a telescope or a microscope that views, a frontier. And it's somehow a frontier of highly controlled, complex quantum systems that give us phenomena that we can't prepare in any other way in nature. And so for the remainder of this talk, I'm going to view the quantum computer as this device, and then I'm going to talk about the data that we get from quantum computers and how we can leverage that data with different types of artificial intelligence, particularly language models. Any questions about quantum computers? I assume there will be lots or none going forward. So let me not say any more about the motivation behind a quantum computer and just say, okay, we're building these things and they produce data. What does the data that comes out of a quantum computer look like? We're all data driven, perhaps, since we work on artificial intelligence. Here's a quantum hard drive. This is my favorite quantum hard drive. This is the trapped ion quantum computing window into the vacuum chamber at the Institute for Quantum Computing, my home institution, where we're building a multi-qubit device that will produce a huge amount of data. Okay, what is a quantum? I mean, you all know this. What is a quantum state of matter? It's a wave function, or maybe a density matrix, but let me imagine I have a wave function. And if I imagine somehow, I chose this picture because it's a circle. I don't know why. But if I imagine I had a hard drive and I called it a hard drive, and what's different between a quantum hard drive and a classical hard drive? A quantum hard drive doesn't just, have one state of qubits at any time. Here's a bunch of bits. Black is spin up, white is spin down, whatever that is. What a quantum hard drive contains is a wave function, which is, of course, a coherent superposition of all possible states. And I've just written it out, all the coefficients in this, this basis, whatever this chosen basis is. It could be the sigma z basis. It could be the occupation basis of an atom atomic level or whatever, right? So there's, if you have a two-state system and there's n qubits, there's 2 to the n different possible configurations. And, what the wave function is that superposition. Now, the coefficients C can be complex. Of course, that's what's special about quantum mechanics. But in many cases, they can also be real. And if the C's were all real numbers, then really what I'm doing is sampling. I imagine sampling from a probability distribution. Every time I take a measurement, I take one shot of the qubits, whatever they're atoms or they're superconducting qubits or they're ions or something like that. I collapse into one of these states with a probability, as you know from the Born rule, that's proportional to these coefficients. If those coefficients are real, then really what I'm doing is producing shots from a probability distribution. And what I'm trying to set you up for is the idea that we can leverage all of the mechanics of generative modeling, likelihood estimation, things like that, to try to learn the probability distribution that underlies the data from these quantum devices, regardless of what states are prepared. When you LHC folks go to the Large Hadron Collider, I always see pictures of you guys with helmets on down there. So this is my experimental lab. I get to show pictures of me in lab. So first off, this is a picture of the ion trap that we're building at the University of Waterloo, Institute for Quantum Computing, just to give you an idea about what the data looks like coming out of this device. So I'll show you multiple experimental pictures. This is a vacuum chamber. Inside there are qubits that are being prepared in ytterbium ions. A bunch of optics has been stripped off of this thing. You can't even see it now if you go into the laboratory. Ultra high vacuum room temperature, RF control for the for the ions to keep the ions in the trap. They're in a one-dimensional chain, and you get single snapshots off a CCD camera that basically look like this. So they're kind of noisy. There's some noisy pixelated, noisy pixels around it. But you can clearly see the atoms. There's one missing here in the trap. That data comes off of these devices with a certain frequency. The raw data that we use when we train generative models, in some sense, looks just like this. And I imagine training models using a data pipeline. This machine here, we're trying to build an open source pipeline. So it's an open source device. The design is housed under an open source foundation called Open Quantum Design. That device, which is open source and design, gives rise to open source data sets. And what we're doing, and what I'll talk about in this talk, is training open source models off of that data. So that's just my ion trap. Here's my LHC equivalent picture that I'll talk about. So the trapped ions are one amazing platform. What I'm going to talk about next is neutral atom platforms. So this is a machine in Boston here. I took this picture a couple of years ago with my student, Roger Luo, who worked on the control system for this device. I'm probably violating multiple NDAs. So maybe I'll just won't say any more about that. And if you're probably also used to quantum computers built on superconducting hardware. So superconducting circuits like IBM, Google, other companies like that. There's many different, I guess, features, there's pros and cons of all these different types of quantum computers. They can prepare different states of matter, of course. They can prepare different dynamical circuits. They have different connectivities and things like that. But one thing I want to highlight is the different shot rates between them. So the shot rates are, when I talk about going back here and taking one measurement of the quantum state, I collapse the wave function, I get one of these pictures out or one of these pictures out. They come off the device at a certain rate. Neutral atoms, although there's been, I think, a lot of advances, are relatively of the order of 1 shot per second. Maybe a little bit faster, maybe a little bit slower, depending on the size. One of the main reasons that of the slow shot rates of the neutral atoms is the procedure by which they're measured, blows some of the atoms out of the traps, so they have to be reloaded. There's been a lot of progress on that front here in Boston recently. Trapped ions are atoms where of course, an electron has been stripped off to make it an ion. That ion can then be held in an electrodynamical trap, which has I guess, like imagine a deeper potential holding that ion in. Optics then turn that into a qubit. Measurements can be made of the quantum state without destroying the atom array behind that, or the ion array behind that. That gives you faster shot rates, maybe 100 to 1,000 shots a second come out of these types of devices. Superconducting circuits, these are solid state devices working at much higher frequencies. You get 10 to the 6, maybe 10 to the 7 shots. We live in a world now where we're starting to accumulate fairly large data sets from these types of devices. So superconducting circuits, I think there's a lot of data being produced, for example, by IBM, Google, and so on. Trapped ions, probably the leaders are maybe IonQ, Honeywell, and the academic labs, and then neutral atoms, which I'll talk about next. So I think we're now preparing quantum states with high fidelities. They're under high degrees of control, and they're producing a lot of data. So what do we do with that data? Is there some value that we can ascribe to that data in all of these different cases? So what I'm setting you up for is the idea that we're going to use that data to train models. And of course, it's not my original idea, but I think a lot of people have now thought about using data as quantum computing data for training. This is the famous stage of the theater at the Perimeter Institute for Theoretical Physics, where I was sitting in a talk by John Preskill recently, and I just snapped this photo. So, forgive the potato quality, but he was talking about AI and quantum computing, which I think is, of course, a hot topic for a lot of people. But he said something which I agree with. Okay, number one, AI may drive future progress in strongly correlated, chemistry and material science. That's the idea of emulation. The idea that we can solve the Hubbard model or solve some quantum chemistry electronic structure problem by emulating it on a device. Okay, maybe. I'm a skeptic, but that makes a lot of sense in some sense. Eventually, quantum computers can accelerate progress by providing abundant training data. This I truly believe. I believe that the devices we build today, in some sense, their sole purpose should be to provide training data for models. The models can be manipulated, they can be measured. You can essentially do everything to the models that you could do in the experiment, plus some, is my argument. And so I guess this is my call to action for us to build open source data sets built on the output of these devices so that we can train generations of models going forward. So I'm glad John agrees with me. Well, thanks. It's great. Let me set the stage for how that looks, then I'll go into the second part of my talk. So I think we all, hopefully at IAIFI, maybe understand kind of roughly how generative models work. Let me set the stage for likelihood estimation. So the idea that I'm learning from data. I have my black box, which is my laboratory device that produces bit strings. If I have n qubits, I have a projective measurement here, x1, which is of dimension n, and is one of those. I won't go back to it, but it's one of those snapshots that's coming out of my device. I can produce a corpus of data that is basically how many vectors of these do I have time to pull out if I'm getting 1 shot a second, and I run my device for. It's more about how long can you make your grad students sit in the laboratory, right? So if I can make them sit overnight, maybe I can collect, 24 hours worth of data. And then, I guess the procedure I'm following is training a model from that data. And so the idea behind likelihood estimation is really that you have some parameterized model. We know all sorts of parameterized model. Restricted Boltzmann machines work really good. You can have autoregressive models. You can have all sorts of different types of architectures. And the goal is, you take those architectures and you encode a probability distribution, or you parameterize a probability distribution in them. And then you want to make the probability distribution match as close as possible the probability distribution that lies inside that device. So that's the Born rule distribution, if you will. Let's just quit. Check. Going good. Now I won't get into maybe the philosophy of that P of X, but we kind of assume that there's an underlying distribution that we draw from. Now, if you think about the internet and the data, the corpus of data that's used to train language models, I think it's fair to ask, like, what is the probability distribution that underlies all pictures of dogs on the internet? Which quickly makes you think that maybe there is no ground truth for this in some cases, but I think in physical systems and quantum mechanics, we're fairly safe in imagining a ground truth distribution. We have a typical loss function, Kullback-Leibler divergence, that we turn into something like the expectation value of the log likelihood, and we do some gradient descent. Simple enough. Everything I show now is going to essentially fall within this training framework, with the exception that, when we have something like a quantum computer, we have another ingredient, kind of another prior that we can think about when we train models. And that's really knowledge of the interaction. I mean, the interactions that occur between qubits. We put in so much effort experimentally into controlling qubits, that we essentially know what the Hamiltonian is in some way. Or we have a pretty good idea of the Hamiltonian that we want in this device. And so another way of imagining using models, which is different than the data training paradigm, is to think of a variational training paradigm where essentially my loss function is just traded, from the log likelihood to something that is like minimizing a free energy. Just think of it that way. In order to define the free energy, I define the target Hamiltonian, and maybe I have to know something like the entropy if I'm at finite temperature. But as long as I think I have a pretty good prior knowledge of the interactions underlying the device, then I can train my models in a different setting, this so-called variational or variational Monte Carlo setting, where I calculate the expectation value of the target Hamiltonian in the instantaneous model parameters and then variationally optimize. So I'll show a couple results for that, but I just wanted to give the idea that I think there's a lot of different flavors to how we can train these generative models when we're dealing with physical systems where we both have data and we know the underlying interactions, or we believe we know the underlying interactions that data results from. Question?
Hi. So the entropy that you have here, this S in the
That's a thermodynamic entropy.
Thermodynamics.
Yeah.
But is there still learning from the quantum computer?
Is it what?
Is there still learning from the quantum computer in this approach, in this free energy approach?
If I'd never had I've kind of bastardized the quantum computer and some classical training. If I had a true quantum device operating in a closed system, there is no concept of temperature, and I would just throw away that entropy piece. If I had the Gibbs ensemble and I somehow warmed this up, I guess I would have to know the temperature, and I'd have to be able to calculate the entropy from the data, which is typically intractable.
I see. So it's a separate approach where you just learn separately with VMC the ground state, so you don't learn the quantum computer in this approach.
Right. Yeah. Sorry.
Oh, okay.
Yeah. Yeah. So the data. Yeah. Okay. The data-driven approach is the top line.
Okay, I see.
I have a laboratory that produces data. That's a top line. If I'm sitting in my theorist office and I think I know what's going on in the quantum computer, I plug that into the target Hamiltonian. That's the variational approach, right? Okay. But I'm going to show that you can combine them. That's the point. Oh, right. I can combine these two approaches.
Thank you.
No, thanks for the question. Yeah. So let me go back to the data-driven approach. I have a quantum computer in a laboratory. It's producing shots. I stripped out a bunch of slides for this audience about exactly how generative models look, and the picture of Hopfield and Hinton, I threw it away. So apologies to my boss at the Vector Institute. But I think we all kind of understand the concept of parameterizing a distribution. We use autoregressive models, which I think probably are fairly common here. The only thing I'll say now is that if I translate between training an autoregressive model and a corpus of data from the internet, or if I train an autoregressive model from qubits in a quantum computer, there's basically no difference besides something like, for example, the dictionary, right? Of course, these dictionaries are embedded. They're not this kind of raw dictionary like this if you train a transformer. But really, the idea behind an autoregressive model is that, you know, I have, you know, hickory dickory dock, and I want to predict the next token in that sequence. That sequence is defined by this, you know, chain rule of probabilities. I have a joint distribution, right? And I've broken that up into a product of conditionals. And the beauty with autoregressive models is you can perform sampling down that chain without a Markov process. So there's no Markov chain, there's no autocorrelation time. There's other amazing features of it. So if I have if I have a quantum wave function, I can, you know, tokenize the output. It's just zeros and ones. I have a one hot, you know, this is spin pointing up, spin pointing down. I don't know what I did here, but you can imagine that I take my qubit data, I tokenize it, I can embed it in the same way. I can also combine phase information. So if I don't just have a probability distribution, I have complex coefficients. I can handle those. I'm not really telling you how, but I can train the full amplitude and phase of a wave function using data in different bases. And really, the spatial dimension of the qubits doesn't matter. You know, in an autoregressive model, even though you have a sequence, really all you do is you kind of pick some arbitrary way of embedding that sequence in the spatial manifold. So there's a few caveats with how you might embed. Here's a 1D system. Here's a 1D embedding, a 2D system with a 1D autoregressive sequence going through it. But these are all details I'm just mentioning so that you can ask me about them later. Everything that you know about training RNNs, transformers from data, you know, that you get off the internet, pictures of cats and dogs, translates directly into training data from a quantum device. Okay, so that's the setting. Now I want to show you some examples of how we've trained generative models off of real quantum computing data that has come from Rydberg atom arrays. So any questions maybe before I go on to show some real data here? What am I doing? What am I doing with my life? Okay. Okay, so let's see this in practice. Okay, Rydberg atom arrays. All right. I don't know. When I talk to the trapped ion experimentalists at Waterloo, and they boot this device up and they trap some ions and they get some data, you know, they're like, every time I turn the switch, there's 10 Nobel Prizes have gone into this device. At least, you know, think about the number of breakthroughs, and am I right, in optics and, you know, optical tweezers in these cases. All of these breakthroughs have kind of, you know, cumulatively allowed us to control qubits. And it's just really incredible to see all this. So in these Rydberg atom arrays, it's no exception. There's amazing experimental and optical and RF and all sorts of different protocols have gone into these things. You can load individual atoms. So they're neutral. Rubidium is, I think, the most common one, rubidium-87, into an array formed by optical tweezers. So you're literally grabbing these things in a vacuum chamber. They're called Rydberg atoms because the atoms can be in their ground state or they can be excited into a high principal quantum number state, n between, I don't know, 50 and 100 or something like that. I'll show you why. They form a strongly interacting quantum many-body system. Not only can they be highly controlled, you can produce single atom resolved fluorescent images, which form our data set. So here's the positions of some atoms in a two-dimensional array. Beautiful image comes out. Do a bit of processing, you get ones and zeros. Boom, I can turn that into my training data. And, you know, I'm just glossing over what these things are useful for, but I kind of motivated the idea that these things can be simulators. They can be used to do combinatorial optimization problems. They can be used for all sorts of interesting things. So we're focusing on the data. Now, the Rydberg atom arrays are special because, number one, they're super highly controlled, perhaps the most pristine, coherent devices ever built. And they have a Hamiltonian that underlies the interactions between the atoms that we think we have a very good handle on, you know, for the last, say, 20-some years. This is the Hamiltonian. Just to kind of think about it in qubit language, we've written in terms of poly X operator, which is, you know, this Rabi frequency promotes transitions between what I'm calling the ground state. So the electrons are all in their ground state. to a highly excited Rydberg state R. Okay, so that's like the off-diagonal matrix element of the Hamiltonian matrix. The detuning off resonance is kind of what biases you. In this case, if I have negative, if I have a positive delta, then this operator is the Rydberg occupation. Okay, so Rydberg occupation is counting, or it's promoting excited atoms, and that competes in some sense against this interaction, which is NINJ. So if I have two neighboring lattice sites and they're too close together, there's some energetic penalty for exciting, the Rydberg state of both of those atoms. And so that competition, in some sense, is what leads to this highly correlated quantum system. For maybe the quantum Monte Carlo experts out there, the Hamiltonian is what we call stochastic, which is a real word. I don't know what it means. Quantum stochastic, which means it has no sign problem. So that gives two important features. Number one, it allows us to perform world-line quantum Monte Carlo exactly. So we have exact samplers for the ground state of this, and actually any Gibbs or thermally distributed state. And we have very good quantum Monte Carlo algorithms for this system. But also in terms of the data, if I have a stochastic Hamiltonian, so I have a Hamiltonian that's all the off-diagonal matrix elements are, I got their sign wrong, but they're all non-positive. The ground state, or the extremal eigen vectors in that basis, are all real and positive. That's apparent for Frobenius theorem. So in particular, it means my ground state wave function is real and positive. So it's directly related to the probability distributions that we're talking about just through the square root. So that's important for the data. We've done a lot of work on figuring, elucidating the phase diagram, the ground state phase diagram of this model, using these conventional quantum Monte Carlo simulation techniques. So I showed you that experimental phase diagram previously. Here's kind of the theoretical phase diagram. There's some boundary issues and all sorts of interesting stuff. But I'm really thinking about, the quantum phase transition between this white state, where I have a small delta, so I have many atoms in their ground state, to one where I have a larger delta, which energetically favors Rydberg atoms. And what you do is you cross that 2+1D Wilson-Fisher fixed point, that quantum phase transition, into what we call the checkerboard state. So this is fairly well sort of sorted out. Jim? Oh, yeah, yes. Thanks for reminding us.
Stochastic. Is this ground state property almost the definition of what you mean by stochastic, or is there something else I should keep in mind?
I use it for the Hamiltonian stochastic, but I think it's a matter of taste.
So a Hamiltonian is stochastic if the ground state has this property.
No, I got it wrong. The Hamiltonian stochastic if all the off-diagonal matrix elements are non-positive. Huh? But I forgot a minus sign here. So there's a simple unitary transformation that changes the sign here. So any Hamiltonian that has a single qubit off-diagonal operator can be made stochastic with a simple unitary operation. Where you get non-stochastic Hamiltonians is where you have two-body off-diagonal interactions, and they're typically on a non-bipartite lattice. So if it's a triangular or a Kagame, Heisenberg model, that's where you typically see non-stochastic. And if you have fermions, you have other problems that are worse than what this definition of stochastic.
And maybe a related question to the ground state property you mentioned. I've heard over the years condensed matter physicists say, suppose that you only have real coefficients in your quantum states.
Right.
But there actually are interesting quantum systems whose ground states there's lots of them that have this property. I mean, it always felt a little cooked up to me, restricting from the complex to the reals. But
well, this is one example.
Okay.
Yeah.
I think that's just a shift in perspective. Thanks.
Yeah. No, this is one example. Nobody can say that this is not an interesting system. Absolutely. I mean, maybe the most hardcore condensed matter theorists, we could solve it all with quantum money. But no, I don't believe that. I believe there are still interesting, unsolvable. Actually, this is very interesting because I'm going to run out of time if I start rambling. But it's actually very hard to sample these kind of long-range interactions efficiently, even with our state-of-the-art world-line Monte Carlos. You need some sort of D+1, I don't know what you would call them, like cluster moves in order to be efficient. So there's also statistical reasons that these types of quantum systems can be hard to sample. that aren't related to the sign problem. So I'm with you. I don't think non-stochastic is the same as interesting. And so here's an example. The ion traps, one reason I'm working on the ion trap system with all my time now is because the ion traps can produce very interesting non-stochastic Hamiltonians that we can't do this type of simulation for. Okay, I got into this whole field thanks to Professor Vuletic and others, but really it was Misha. It was Manuel Andres who got me into this. So Manuel Andres had done the loading, the loading algorithms for these atoms. And I was, of course, in Santa Barbara, where I always am. And Manuel had invited me to give a talk in Caltech, and I was too busy. And so I sent my grad student, and Giacomo Torlai. And he went down, gave a talk, and came back. He's like, you got to see the data that's coming out of these Rydberg atoms. So that was 2018-ish or something like that. And so what happened was we got our hands on, this is the first data we looked at coming out of the devices. It was 8 or 9 atoms. I put 8 here, so I'm going to trust me. Which, we produced, the experiment had produced 3,000 projective measurements and had swept this detuning parameter delta across the 1D equivalent of this quantum phase transition. And so here's the average occupation. It turns on. It saturates at 0.5 because you get up, down because of that blockade effect, if you will. And just to show this real quick, here's the experiment, which is just the average of a bunch of data points. Here's an exact master equation. This is an 8 atoms, so it's something that can be solved with all sorts of classical dynamical simulation techniques. And here's the trained generative model, the blue. So one interesting thing that I pulled out of this paper, number one, is that the occupation values match exactly what I expect from the experiment. Great, the generative model works. Who cares? Why would I ever train a model off this data? And I think this illustrates it nicely. Think of it as a generalization to another basis. This is the expectation value of the sigma x operator, which is off diagonal. Off diagonal, and again, my data is literally this. If I have an off diagonal quantity in this data, is there an easy way of obtaining it? Well, it turns out in the case where you're stochastic, you can directly take the probability distribution without a phase related to the wave function, do something with your estimators, and directly get off-diagonal expectation values out of the inference phase of this generative model. Think of it like that. So here's a generative model, reconstructing the off-diagonal operators and comparing it to the exact master equation. So I always like to show this plot because when we first did it, there wasn't a great match between the off-diagonal quantity that, again, comes from the trained model and the experimental expectation, which I believe Misha eventually fixed with some detuning control that was a little bit out of whack. So it never made it in the paper. But I really think that this is one nice illustration of how these types of generative models trained from data help us control and calibrate and think about the experiment. So we went on from there. We did a lot of work on data from the 2-dimensional arrays, which are very interesting. Here's that phase diagram that I mentioned, except for Abadi's work. That, again, produced a corpus of data. We used, in this case, a 2-dimensional R and N wave function, which I won't talk about. But, again, the neutral atom experiments are somehow data limited. And they're data limited because, 1 shot a second. Grad students have lives, apparently. They can't sit in the lab all the time. So in this case, we got 1,000 projective measurements per detuning parameter. And if you think about the size of that quantum state, 2 to the n, think about characterizing the wave function on 256 atoms, 1,000 shots isn't enough. You can basically convince yourself that you're not going to cover all of Hilbert space, enough to to characterize the data. And sure enough, here's data at that quantum critical point. Think of it as the loss function, but it's really the loss function of the energy. So this is the expectation value of the Hamiltonian. What happens is, using, again, this is straight up data-driven density estimation. We start training our model. It plateaus. I know the exact ground state, I think, from the quantum Monte Carlo, and then I start to overfit. So a big question that we asked was, well, what use is this data? Yeah, you can measure some correlation functions from it and so on, but you can't really reconstruct the wave function from this limited amount of data. And what my student Skylar and some of the other postdocs said, well, compared to the variational optimization. So when I showed those two cost functions, remember I can drive learning with data, or I can drive learning with knowledge of the Hamiltonian. So here's knowledge of the Hamiltonian. Here's that cost function. I threw away that entropy. We're at 0 temperature. This is what I would call variational Monte Carlo. I'm essentially training the same RNN wave function, but I'm doing it variationally using the expectation, using the gradient of this term. And sure enough, this is a valid way of doing simulations. But in many cases in VMC, you see slow convergence, and I would have to run this thing, I don't know, 5 times longer to get decent convergence. So long story short, what we discovered is that if you take the experimental data from the quantum computer and you do the initial batch of training and then switch the cost function. So here at this red line, I have a partially trained RNN. It's pre-training in some sense from the experimental data. Now I switch the cost function to minimize the expectation value of the Hamiltonian. Boom, my energy slams right down to the expected value, in a much shorter time. So one thing we've been pursuing quite a bit is using limited amounts of quantum data to speed up simulations. And I think this is a very general idea. If I had data from a Hubbard model in various bases, I could speed up a variational Monte Carlo of the Hubbard model. If I had data from some other Hamiltonian, again, I could speed up variational Monte Carlo of that Hamiltonian. And so that immediately tells me that there's value in this data, even though it's not enough to perhaps be informationally complete in terms of the structure of the Hilbert space. So we've moved on from RNNs, and we have, in my group, been training, I guess, more modern models. This is our favorite model called Rydberg GPT. I've been showing this model for a little while now. This one has 66,000 trained parameters. It's an encoder-decoder model. I'm sure you've all seen this type of plain vanilla transformer. Sigma is my X. So these are shots from the quantum computer. There's an embedding. They get fed into this decoder, and out the top comes the conditional distributions up top here. We've conditioned this on a context that comes through an encoder, and in that encoder, we've encoded think of it as the experimental knobs. It's the Rabi frequency, the detuning, even the interaction matrix. I have all sorts of things that go into the encoder. So now I can get pairs of encoder-decoder input, a shot that comes from this experimental parameter. I train this model, and then after that model's trained, I can perform inference on that model, just by varying the inputs to the encoder. Will that work? I was actually really skeptical, but when we trained it on data, now this is near the quantum critical point here, we found what I'm going to call generalization. This is really out of distribution generalization. So here's the energy. Here's this is like the stagger magnetization. This is more like a plot we've seen before. I've trained this model on data at the red points, and then I performed inference at the blue points. So the blue points are inference from a model using Hamiltonian parameters that the experiment has itself never done. The experiment has never looked in this regime of delta 0.5, whatever RB I'm at, and so on. But in this case, I know the exact answer from my quantum Monte Carlo, and so I can argue that diagonal, off diagonal, these quantities generalize very well. So for me, this is a very, I guess, enticing case for how to use, in this case, a transformer-based, attention-only model, in conjunction with quantum computing data. It's because those experiments are very expensive, both in terms of, cost, but also grad student lives. And so what you want to do is minimize that cost. And so if you can train a model that can be generalized sufficiently, you can explore different parameters of the quantum device, just by tuning the input to the encoder. And by the way, this is trained on one A100 for 85 hours. We have a variety of models. And so what we're doing in my group now is we're scaling this up. We have more data. We have an open source data pipeline. I have more GPUs, thankfully. I have more GPUs, thankfully. Maybe if I stand here. So again, this I think kind of exemplifies what we want to do with our models. I'm almost out of time. Any questions on Rydberg atoms? All right. Okay. More data, more GPUs. What's the third ingredient? I forget. More parameters.
Looked pretty good.
Right. It's pretty good, but there's a massive parameter space in the experiments too, right? So fair enough. And what I mean, use our imagination. I want to build a digital twin that's generalizable. You know, the quantum computer has a lot of parameter space, more parameter space than you ever have time to, you know, really study experimentally. And data is expensive. So I think the long-term goal is to build models that scale. I really want to build a scalable model. And so maybe that leads into my last point. Okay, so if nothing made sense, question? Yeah.
Sorry to derail you.
No, not at all.
Just a question about the stochastic assumption. So in the case where, if you wanted to study something where it was not stochastic and you did the worldwide Monte Carlo, and you do have a sign problem, couldn't you play the same game but just do the usual phase reweighting and just crank up statistics, or does something else go wrong?
Well, the variance of your expectation values explodes exponentially with size and inverse temperature. So there's an exponential wall in calculating estimators from a non-stochastic model with conventional Monte Carlo.
So it's just very hard. Okay.
Yeah, you could try. And people do it on small system sizes at moderately high temperatures, and you get decent estimators. But for example, if you want a ground state property, forget about it. It's basically beyond our computation.
All right, since we're asking questions, I'm trying to understand this conceptual, like, why is the data like learned so fast, right? Compared to, you know, some sort of just, you know,
Hearing
physics, yeah, some inductive bias, right? Like it makes me think that the data somehow is like, I mean, because the data seems to be dependent on the experiment too, right? Like it seems like your model is like way too expressive, right?
I show this because of that question. I don't know the answer. And by the way, if I train in different orders, this doesn't work. But think of the quantum computer as a black box with ground truth in it, and you know, I'm sampling from that probability distribution, right? I'm getting real samples from that probability distribution. Those samples, you know, pre-training on those samples seems to be better, you know, starting from a random initialization, than doing a variational or a physics-based optimization with using knowledge of the Hamiltonian.
Yeah, I mean, my question is like, if I took some aliens who didn't know how to use, or like accountants or something, who didn't know how to use a quantum computer, and I told them to run the experiment, would you have the same convergence, right? Like somebody who, is this just the quantum device you're learning, or you're learning like secretly the fact that you have experts who've spent like years tuning these machines?
No, it has nothing to do with that.
Okay.
If you just get raw noise, this is noisy, this is just raw data, no post-processing at all on this.
But
We just chose it out of a corpus of data at one particular point in the phase diagram and trained a model.
okay, so
That's it.
it's really just that it's like it's learning the quantum mechanics.
Yeah.
Okay.
Yeah, an alien, which is me, I'm a theorist, who knows nothing about the experiment, could do this. Yeah, it knows nothing. So I'm rambling.
Related. So for the data, did you try, like, what is the dependence on statistics here? So if you had less, if you gave it less of these measurements or more of these measurements, and then switch the training to the theoretical loss function, did you see a change?
This, if you have more measurements, this orange curve moves down.
Yeah, okay,
Yeah.
that's what I would expect.
Because again, the idea is you're basically not informationally complete with you only got 1,000 shots, but you got 256 qubits. It's just not enough to cover Hilbert space. You don't have enough information in the data to get you anywhere near the actual ground state. Yeah. And in this case, here we had enough data. So 3,000 shots for 8 qubits is enough. And so I didn't show the same plot because it all converges nice. Yeah. But when you have limited data, which, you know, eventually as you go to more and more qubits, you're always going to be data limited in that sense. You're never going to have a complete coverage of the Hilbert space to do this. It's like tomography. You can never do full tomography when you have hundreds of qubits.
Technical question. So your system is two-dimensional, but when you look at it, you pretend it's 1D and you snake through it.
Yep.
So do you know how bad this is, or why it's not bad? Because I would expect
Yep.
a short.
We've done a study on all the, you know, many different possible autoregressive paths. Some are better than others, but they're usually better in the sense of time to convergence. So if I have a better autoregressive choice of the snake, I typically converge faster, but the quality of my minimum is the same. And if you go back to this equation, I mean, this is completely general, right? So generally, I can have any arbitrary autoregressive path, and I'm correctly represented my joint distribution. But
Practice, do you change among them, among the paths while you train, or you stick
no,
to one?
no. You can do that. We usually stick to this one because it's the one I know best. But there's a whole field of study that I think people haven't looked at with these autoregressive paths. And we tried these as they're called Z curves, these locality preserving Hilbert curves or whatever they're called, and they actually work worse for these models, and I don't know why. Because in other fields of simulation, tensor networks, those tend to work better. So again, I'm just giving you guys ideas for projects here. I have no idea. We have very little knowledge about how, it depends on the entanglement, really. The entanglement structure of your qubits. You have long range entanglement all over a two-dimensional array of atoms. And in the case of the RNN, which we used here because it was many years ago, we pass the hidden vector in kind of a geometry that makes sense in terms of the spatial locality and so on. In the transformer, it's different. When you have the attention, right, you have all pairwise couplings, and it's just a different way of thinking about it. So who knows? I'm glad you're interested. It's a wide open field. Question at the back? I'll repeat the question. Go ahead. Okay.
Thanks so much. Have you thought of a way of getting insights on the effective experimental Hamiltonian?
Oh, 100%. Yeah. I mean, in some sense, that's what this is here. This looks like the experimental Hamiltonian lines up with expectations. But then when we look at off-diagonal quantities, obviously there's something stuck in the detuning. So that point right there tells me that the experimental Hamiltonian is not exactly what the experimentalists thought it was. That's just one example. But yeah, I think quite generally the idea that you have access to all sorts of, anything that you can calculate, any estimator you can calculate in Monte Carlo, including things like the second Renyi entropy or highly non-local things like that, you can calculate in the models that are trained like this. So you can take data in whatever your informationally complete basis is, train a generative model, and then calculate the second Renyi entropy from that model, which is completely basis independent. And that tells you a lot about your experiment, for example.
Thanks.
All right, well, we're out of time, but I saved the best for last. I'm just going to blast through something that we've been doing over the last couple of days. Critical points in universal scaling. Back to the quantum critical point. My goal is to prepare some unique quantum critical point in maybe the ion trap, produce data that can, no other device no simulation on Earth can spoof it and so on. And try to scale a model up. What I haven't talked about is scaling. Thanks largely to the string theorists I met in Santa Barbara recently, we started thinking about the data covariance matrix. Here's the data covariance matrix is the outer product of your data vectors averaged over all the vectors. You've probably seen this all the time. This is what they call the centered data covariance matrix. It looks just like a connected two-point function. I'll get back to that. The covariance matrix of natural data often has power laws in it. Have you heard this before? Nature sits in a critical point or something, but does it? But there's power laws. Here's MNIST. MNIST is a pretty nice power law, but it has this is like I'm going to say it. This is like the UV cutoff, or it's like a UV tail here. Here's actually the data covariance matrix from the Rydberg atom data. I can't remember. This must be simulated data now that I look at this, but it's at the quantum critical point. It's almost a perfect power law. So we started asking questions. This is Skylar Moss and Yihong Hale, who have started asking, what's the relationship between the quantum critical point that we can prepare in this quantum computer and these power laws, and what's the implications for scaling? Very quick for the condensed matter, or maybe the CFT people in the audience. So my data covariance matrix, what I'm plotting really is the eigenvalue spectrum. Here's the eigenvalue spectrum of, now this is simulations of the 2D Ising model. I literally did this over the last 2 days. on Yihong's broken down laptop. So there's xi, xj, that's just the vector, I have different sizes, and I'm just taking the vectors, taking the outer product, calculating the expectation value, calculating that matrix, and then doing the eigenvalue problem. Here's my eigenvalues. And the assumption is, and the observation is that these decay as a power law when you're at a critical point. And we've confirmed this. And this is what that typical power law looks like. Now, if I take that power law, I can fit out alpha for various different system sizes, just some standard finite size scaling, and get a pretty good estimate of my alpha here. What should that alpha be? Is it related to the critical exponents? That was the question. The answer is yes. The way you see this is by the common condensed matter trick. You assume translational invariance. You go into Fourier space. You realize if this is my 2-point function, I've just called G of K my momentum space 2-point correlation function. This 2-point function diagonalizes that matrix. So the eigenvalues of the matrix, of the covariance matrix, are G of K. They are the Fourier transform of the 2-point function. And that's good because I don't have any connection between the eigenvalues in real space, but I do have this direct connection between the Fourier space 2-point function and the eigenvalue. So this is really an ordering. And again, this relies on translational invariance, but it's all a finite size effect. This is ordering in terms of momentum. So you can always think of it like this. If I assume that, I take my G of K, K is my momentum. This is the scaling estimates for the critical exponent eta. And then I can relate the eigenvalue spectrum directly to that. I have to integrate through the density of states in momentum space. This is alpha. This is some finite size scaling. If I put in the 2D Ising model, 0.25 and 2 for these critical exponents, I intercept exactly that value at the thermodynamic limit. Why is that important? I think a lot of people think about the power laws in this covariance matrix and the consequence for these types of scaling laws. And I particularly like this paper. Dan Roberts, is he here? MIT, just checking. So they have really nice kind of phenomenological models of how these power laws in the covariance matrix lead to these scaling laws. And so for a pure power law, which I believe, I don't know how to prove it, but I believe exists, if you think of this momentum space argument, at these critical points, I think, there is no cutoff. You get bigger and bigger in system size, that UV, you keep pushing that, down and down. I think it's just very natural to directly relate that to LLM-like laws. And so you can recognize these as scaling laws, probably. This is a loss function. N is the number of parameters, I think. T is the amount, it doesn't matter. It would be symmetric in this notation. What we're doing now is we're just confirming these simple models, but I believe models, LLMs, transformers, trained on data from a quantum critical point. And a quantum critical point's important because, again, this dimension might be d plus 1. Or if I have a deconfined critical point, this eta might be order 1 instead of order 0. So there's very clear signatures of quantum criticality in these universal exponents. I believe those will be reflected in the scaling laws for the LLMs. So right now what we're doing is we're producing a bunch of synthetic data. We're going to train a whole bunch of transformer models, and we're going to look for critical exponents, like real critical exponents in the scaling of those models. So that was the last part of my talk in 5 minutes. So if you have any questions, happy to answer them. Just in summary, again, I'm always trying to convince the experimentalists, just produce the data, produce a corpus of data. We'll tokenize it, we'll train models. Those models can be used to measure things that you can't measure experimentally or you can't easily access experimentally. They also generalize well, especially this sequence-to-sequence encoder-decoder model that I showed you. We can take a bunch of data, we can train some models. They seem to be able to generalize in experimental parameter space. We can even drive those models variationally. That's how you do quantum simulation. You take data, you take knowledge of the Hamiltonian, you have AI models, the whole package. And back to my, my motivation. We're not building, or I'm not interested in building a quantum computer to break 2048-bit RSA. What a quantum computer is a telescope into a new frontier. Quantum critical points, I think, are some of the most exciting aspects of that frontier. Everything lines up. It's very natural to imagine preparing a new unique quantum critical point, getting a whole corpus of data from it, training a model, looking for scaling laws, etc. I hope I got you a little bit excited about this too. Thanks very much for your attention.
Are there any reminders?
Fascinating.
Thank you.
Great. So I wonder, how does the quality of the data affect your solutions or your conclusions? I mean, so far you've trained on kind of 1% error data.
Right.
When we now use error corrected data where we reach, 10 to minus 5, 10 to minus 6, what influence or, what other consequences for your program?
I think we're fairly robust to noise. In this early data, we did have a noise channel, an asymmetric noise channel for the measurements. I forget what it was, but zeros could be ones and ones can be zeros with different probabilities. We actually just put in a conditional layer to reflect those probabilities, and I think it worked pretty well. It seems to be highly tolerant. Now, one thing with the superconducting qubit data, if it comes out of IBM or some of these other big machines, they might be getting 90% bad shots instead of 1%. At 90%, I think you're gonna have a situation kind of like this. But this can also be an error mitigation technique, right? So if you have a lot of bad shots, high number of bad shots, but you're fairly confident in your interactions, you take that data, you do a bit of variational driving, you can easily mitigate that data. So I think it's actually made for noisy data. No, thanks for that question.
I also have a question with this slide. So what's the purpose of doing this? Do you put this do you have it in mind as an analysis tool for the experiment? So experiment gives you data, you want to extract structure from this data, you do this or not? Because I get the feeling that, okay, you pre-train with the data, but then you minimize on some Hamiltonian, which in the end, the experiment might not realize very well. So you end up doing theory instead. So this experiment.
You bias. I mean, it's all about the prior. Think of it as do you really know the ground truth of anything? No, of course not. Right? The purpose is you have a prior and you can evaluate the prior. Put it that way. The data's evidence, I'm talking Bayesian. I think the Hamiltonian, that structure of the Hamiltonian is the prior. If you get that wrong, you're biased.
Sure, but then in principle, I could initialize at random, and when I put in the Hamiltonian, I would converge the ground state regardless of my experimental data. So
you will, but you won't. So in practice, the blue curve, that little bit of energy is actually a lot of energy. There could be completely different correlation functions here. And that's the scourge of variational Monte Carlo. Certainly in my field, my advisor never ever used variational Monte Carlo. Scalapino was a Hubbard model guy. He did not believe in variational Monte Carlo. And as we transitioned into topics like spin liquids, it became very apparent. Spin liquids, they're very subtle correlations, and any energy gap like this completely blows those correlations out of the
I
water.
agree. I just would say at the bottom of the green line, you are in a theory ground state, not in an experimental state anymore.
You're in a combination because you don't get there unless you have experimental data.
So if your Hamiltonian is a prior, can I also update my information on the prior with the data that I learned from the quantum computer?
I think so. Yeah. That happens all the time in an experimentalist mind, right? So it's true. No, absolutely, 100%, absolutely. Yeah. I think that's maybe one of the main points of the whole, at least at this stage of things, right? Is like, here I have a prior, here's my exact diagonalization. In this case, only uses knowledge of the Hamiltonian, does a master equation on it, right? That prior doesn't fit that data. This isn't a deficiency of training or a deficiency of the model or under parameterization, right? That's up. You have to update your prior about the Hamiltonian at that point. Jim's champing at the bit here.
I'm going to ask a question. I don't know if maybe I'm champing. I'm just curious if you could say a little bit more about the stuff at the end. There's scaling laws and language models.
Yeah.
Quantum critical points have scaling laws. I think I missed how you're gonna put them together.
Quantum critical points of scaling laws in the covariance matrix.
Yes.
I don't know if that translates into these scaling laws. Into now, what do you call these? LLM scaling laws, right? I don't know. But there's simplified models where they do translate. And there's quite a bit of work, I think, that follows up on this that takes data covariance matrices, that's what we have here, and looks at power laws in those. And so the argument has always been that like real data, it doesn't have a pure power law. You have something like this and MNIST, CFAR10 and something like this. Somehow, if you look at the data covariance matrix of a feature space, then oftentimes you get better power laws. And so, you have your UV, I don't know, you have some feature space. That feature space, if it's power law enough, I guess one hypothesis is that leads to LLM scaling laws. My argument is, I mean, I haven't trained him yet. This is like literally, I made Yihong send me this data last night. I'm like, I believe that if you train models on this data, you'll see scaling laws because it's such a simple power law. Bigger and bigger sizes, you grow your corpus of data. You start training more data, more parameters, more.
So the hope is training ever larger language models on data that itself has its own power laws is gonna somehow the power lawness is gonna translate and connect.
I think the critical exponents, the physical critical exponents in the RG sense, whatever you want to call them, those will translate into the power laws in these curves.
Okay, so you think alpha will be a function of the different scaling in the system associated with spatial scaling. Those critical exponents, you think that alpha will be a function of that.
I'm saying it here first at MIT.
All right.
That's my prediction, guys.
Roger's prediction.
That's my prediction. So invite me back in a year. That's very kind.
I'm interested in learning a fermionic wave function, like some actual chemistry problem.
Yeah.
I need to learn the sign structure.
Yeah.
Does that work? Like because.
Yeah. I mean, work. What does that mean? So amplitudes are easier to learn than phases.
Yeah, exactly.
For sure. I think we have lots of evidence of that. If you have a judicious choice of basis, then you kind of, if you get most of your, your amplitude captures most of your information, that's always the best strategy. I think it's just an empirical fact that either the sign or the phase seems to be harder to learn. So, yeah. If you can, we talked about this, some of us before, but like, any Hamiltonian can be made sign-free if you know the unitary transformation. So you can translate this question and can I learn a unitary that unties the sign structure? Right. And then you can take that unitary, decompose it into gates. Those gates have some parameters. Can I learn those? We've attempted that multiple times on different systems. There's easy problems and there's hard problems there.
Interesting.
So there's probably a way of classifying your sign structure more in that philosophy. Something that's easy to learn, something that's hard to learn.
I mean, if I have a topological, if I have a vortex or anything, I cannot unwind it, no matter what's the.
Double semyon. If you think of the double semyon wave function, you have a minus sign in front of, it's a loop gas, right? If you have an odd number of loops, then the coefficient's minus. In the toric code, all the coefficients are positive. So if you wanted to untie the sign structure of the double semyon, it's highly topological. I think Hastings is a proof. I mean, it's basically a topological proof that that's hard. So I think the double semyon and related wave functions are believed to have an intrinsically hard sign problem. Thank you very much.